Hello, thank you for joining me. My name is Lucas Ehinger, and today I'll be presenting on a theoretical physics research project I did into the light C quark asymmetry in the proton under the supervision of Dr. Mary Alberg at Seattle University. So I'm going to begin with a basic overview of particle nuclear physics, focusing in on the proton. So, as you know, an atom is composed of protons, neutrons, and electrons, and we can even zoom in on like a proton and a neutron and see what that's composed of. And protons and neutrons are composed of what we call quarks. And here we work with two main types of quarks, up quarks, which are designated with a U, and down quarks, which are designated with a D. So the proton is composed of what we call three valence quarks, that's two up quarks and one down quark. And these three quarks are kind of the base constituency of it. In addition to this, we have these particles that essentially hold the proton together. So that way these up quarks and down quarks don't go flying away and so they stay together. These particles, we call them gluons because they essentially glue the proton together. And finally, we have quark-antiquark pairs. So a gluon at any point in time can split into a quark and an antiquark, or vice versa. And an antiquark, for example, right here, this is an anti-up quark, which is the antiparticle of an up quark. Same with a down and an anti-down quark. So we know the proton to be made up of these valence quarks. Then we also have gluons, and we have quark-antiquark pairs, which we call C quarks, because there are just a lot of them that are constantly popping into an atom existence, kind of like a sea of quarks. So we started out by trying to recompose the proton using a statistical model developed by Zhang. And in this model, we consider three reactions. We have a gluon that can split into two gluons. We have a quark that emits a gluon. And we have a gluon splitting into a quark-antiquark pair. So right here, this could be an up quark, it could be a down quark. Same with this one, an up or down quark-antiquark pair. And looking at these three reactions, we then look at all the different states of the proton. So our kind of our smallest state are just the valence quark, just our up, up, down. And then we can look at the next kind of largest state, up, up, down with one gluon. And how many ways are there to go from this first state to the second state? Well, looking at this at the second reaction here, we have a quark emitting a gluon. So we can have that reaction happen for any of the first three quarks, which gives us three ways to go from the first state to the second state. And similarly, if we want to go from the second state back to the first state, we just look at these reactions in reverse. So we have an up and a quark, or quark and a gluon combining to only form a quark. And we can have that with a gluon in the down quark, gluon in the up quark, gluon in the other up quark. So there are three ways to go from left to right, three ways to go from right to left. We just make the assumption, and this isn't necessarily true, but we make the assumption that all three of these states are equally likely, which means that since there are three ways to go left, three ways to go to the right, these two states have an equal probability of occurring in the proton. If we now look at the next state up, again, where we have up, up, down, and gluon, and then in this right state we have two gluons, we essentially need to create one more gluon, so we can create that extra gluon using our middle reaction here, just like the last time, or we can have a gluon emitting another gluon. So now we have four ways to go from left to right. But if we want to go from right to left, again, we have this gluon and quark combining to form only a gluon, and we can have that with this first gluon in these three quarks, that's three, or with the second gluon in these three quarks. So that's six possibilities, plus then two gluons recombining. So that's 6 plus 1, so that's 7 possibilities to go the other way. And that means that this outer state is 4/7 times as likely as this left state. And we then went ahead and generalized this method of principal balance to all states containing 20 or fewer particles, so up, up, down, UU bar, up, 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 down, DD bar, and so on up to 20 particles, and use that to determine our initial statistical model. So then we had probabilities of each one of these states where the total probability was equal to 1. As I mentioned, there were a couple of assumptions we made here, like that all these three states were equally likely, so this model is kind of crude. Fortunately, my advisor, Dr. Mary Alberg, came up with a much better model, which she's used previously, where she says that the proton is composed of something we call a bare proton plus Meson-Baryon pairs. So a Meson-Baryon pair is essentially we can view the proton as being a proton, or we can view the proton as fluctuating into different types of particles. So here we looked at it, and initially we looked at it very carefully and looked at the constituent quarks. Now we're kind of zooming out a little bit and saying the proton is sometimes just a proton, and sometimes it fluctuates into a neutron and a pion, or into a proton and a pi naught. So we're kind of taking a step out, and we see these fluctuations due to the Heisenberg uncertainty principle. And what we need to know is what is our bare proton, kind of our starting state when we don't have any fluctuations. And that's what we're going to use this statistical model for. So to do that, we take our statistical model and we subtract out our kind of crude statistical model, and then we subtract out all these Meson-Baryon pairs. So I'm just going to show a quick example of that because this is kind of abstract. But if you think about our up, up, down, D, D bar state. So just like here, we had up, up, down gluon. Now we have up, up, down, D, D bar. And we can view that both as up, up, down. That's our valence quarks, and a D, D bar. So that's part of our just proton. We call that part of our bare proton. But we can also regroup these to up, down, down, and then a U, D bar. And this up, down, down, these are the valence quarks for a neutron, right up here. And this U, D bar is a pi plus. So this exact same state, we can view once as a Meson-Baryon pair on the left-hand side, and on the right-hand side, we can view it as a bare proton. And since we want only the bare proton, we then subtract out these Meson-Baryon pairs, giving us just a bare proton. We then put our bare proton into this bare proton term here and add back in the Meson-Baryon terms using the much better Meson Cloud Model to arrive at our full proton. On the way of doing that, we also need to determine the momentum distribution because all experimental data that we want to finally compare it to gives everything in terms of momentum distributions. And we also needed to evolve it up to higher energies. So our theoretical energies happened at very low. Our theoretical calculations happened at very low energies, and we want to compare it to very high energies. So we evolved it from 2 gigaelectron-volts squared to 54 gigaelectron-volts squared using a program called BF1 with these Altorelli-Parisi equations. Right here in the blue data bars, you can see these are experimental data. The black is the results of the Meson Cloud Model using our bare proton, and the green are the results of the Meson Cloud Model using Sirik's proton, another competing model. And here you can see both models fit the D bar minus U bar distribution pretty well. So on the right-hand side, we have on this x-axis here, we have momentum. And on the y-axis, we have the number of D bar quarks minus the number of U bar quarks. And then this graph here to the right, we have the number of D bar quarks divided by the number of U bar quarks. Same, the x-axis is our momentum. And initially, both of us do a fairly good job of, or both models do a fairly good job of describing the data. However, you can see after about 0.2, we don't do a great job. However, you can see right here in the blue, these are fairly old experimental results, while in the green, these are new experimental results that are hopefully going to be released in a Nature paper in a couple weeks. But these are preliminary, and there is quite a bit of discrepancy between them. So we're not quite sure how our model even stacks up to the experimental data. However, one thing we do know is that our bare proton term is dominating way more than it should compared to these Meson-Baryon terms. So our next step is to work a little bit more with this evolution step to bring it from lower energies to higher energies. And we want to work with that a little bit more to try to fix and reduce the effect of our bare proton. Because right now our bare proton is having much too large of an effect out at large X. And we're hoping that we'll be able to see a little bit more of the effect of these Meson-Baryon terms from the Meson Cloud Model when we fix our evolution a little bit. If you have any questions, please feel free to reach out, and thanks for listening.